Okay, here we've got a dual cycle with all of the parameters already given to me, right? Where I've got temperature, pressure, U, and H. Everything's looked up for me, which is great. You'll remember that a dual cycle is a combination of the Otto cycle and the diesel cycle, meaning my heat addition occurs in two pieces, one with constant volume and one with constant pressure. Everything else is the same. It's just I've got kind of this two-stage heat addition. It kind of is a melding again of the Otto and the diesel cycle. Okay, so there's a few things I need to find out here, and a lot of this, once again you figured these out, there's a lot of plug and chug sort of stuff. For example, my cutoff ratio, by definition, is V4 over V3, right? That is that constant pressure heat addition. So from the ideal gas model, right, PV equals RT, if P and R are constant, which they are, P is constant, R is always constant, then V is directly proportional to T, meaning I can use T4 over T3 to get the same result. And again, I know T4, I know T3, therefore my cutoff ratio is 1.1. So again, once you set these states, life becomes very easy. Now my heat addition, remember this occurs over two pieces. So the first thing I'll do is I'll find Q2 to 3. Okay, Q2 to 3 is that constant volume process. That's where there's no work being done at all. Therefore, that is simply M times U3 minus U2. Okay, and again, that's because there's no work being done. So Q2 to 3 then is 42.19 kilojoules, right? The other heat addition is 3 to 4. And again, with 3 to 4 at constant pressure, that means I do have some work. I have PDV, right, for my work. And now I do have a change in volume times a constant pressure, right? So to find my Q, it's that work as well as the change in U. So PDV and du, well, that's U plus PV, the change in U plus PV, which is the change in H. So I can find Q3 to 4 as just H4 minus H3. Okay. And again, I use the H because, again, I have this constant pressure work happening during this heat addition as well. So I have to have the change in U as well as P change in V. And I get 11.19 kilojoules on that one. Again, mass was given to me. I'm not sure if I stated that. That means the total Q in is just those two added together, which is 53.38. Okay. Q out is right here, 5 to 1. Constant volume heat rejection. So Q 5 to 1 is nothing more than change in U, because again, I don't have any work going on here. Work is 0, therefore Q is just delta U. Okay, so I just use these two guys here, U5 minus U1. So Q out is that, plug those values in here, and I get 20.56 kilojoules. That's how much is going out. Okay. The net work, so the work of the cycle, just equals Q of the cycle, which is just going to equal 53.38 minus 20.56, which equals 32.82 kilojoules. And it's just Q out, or Q in minus Q out, equals the work of the cycle. That's how cycles work. Okay. Now all I need to do to find my thermal efficiency is that work of the cycle that I just found, all over Q in, which I found. Plug in those two values in there, and I get 61.48%. So again, the key thing here, as per usual, is once I set the states, it's just kind of a plug and chug sort of idea. Just remember with the dual cycle that you have two heat additions. You've got a constant volume heat addition, where that's delta U, and then a constant pressure heat addition, which is delta H. Again, because I have some work being done here and no work being done here. That's the difference between the U and the H. Everything else, I think, is pretty straightforward on this.